is a webinar being given by Dr. Fred Kucharski of the Earth System Physics Division at the International Center for Theoretical Physics, Trieste, Italy, on the topic Tropical Atlantic Influences on the Indian Monsoon. It is an ongoing investigation. Fred would like to present. And to introduce the speaker, Dr. Fred Kucharski had his early schooling in Germany. Thereafter, he had his university education at the University of Kiel, Meteorology, with his thesis, a diploma thesis on application of the variation data assimilation technique in a boundary layer model. He finished his PhD in 1997 on the concept of energy and available potential energy, supervised by Professor Dr. F. Herbert from the Institute of Meteorology and Geophysics, University of Frankfurt, Germany. Fred thereafter joined as a postdoctoral fellow with Professor A.J. Todd at the Department of Meteorology, University of Reading, United Kingdom, and thereafter he was a research scientist at the Met Office in Bracknell, United Kingdom, in the Numerical Weather Prediction Division. Worked on the Unified Model Development Group with an aim of improving the numerical weather forecast with emphasis on impact of vertical resolution. Presently, Dr. Fred Kucharski is serving the International Center for Theoretical Physics as a research scientist in the Physics of Weather and Climate Group, Italy. The research comprises the investigation of global climate variability and predictability, including phenomena such as the North Atlantic Oscillation, Sahel rainfall, Enzo South Asian monsoon connections, etc. Dr. Fred, to his credit, has more than 120 publications in standard reputed journals. I'm very happy to once again invite Dr. Fred Kucharski to deliver his talk on the topic Tropical Atlantic Influences on the Indian Monsoon and Ocean. Dr. Fred, welcome.
Oh, thank you very much, Ramakrishna. It's such an honor and pleasure to give this presentation here. So this is a research that I'm following for many years already, but it's still ongoing because there are still many unresolved questions. Whereas the Enzo-monsoon relationship has been investigated for more than 100 years, as you all well know. The tropical Atlantic relation to the Indian monsoon, which is much weaker, has been investigated much less, which is also justified. But anyway, this investigation is ongoing. First of all, I want to thank to Professor Ramakrishna and to Roshmita Panda, who I know both from ICTP connections. So this is my connection to Andhra University. Roshmita visited many times, and we are still collaborating. And also Ramakrishna visited many times ICTP, so we have these good connections. I don't know how this works. If there are any questions, will the questions be afterwards or during the talk?
No, after the talk, at the end of the talk.
Yeah. Okay. So sources of the monsoon variability. This is a long-standing topic, of course, very important for everybody living in the South Asian area. And there have been so many proposed mechanisms. Probably the most famous one is the Enzo-monsoon relationship, where when there is a El Nino going on, then people in India and other places in South Asia expect maybe dry conditions and vice versa during La Nina. But there are so many other possible interferences. For example, the Indian Ocean, of course, has been proposed to play an important role, and it's playing an important role. Extratropical influences, intrusions of air masses from the extratropics that may be regional dependent. And of course, the internal atmospheric variability, which has the disadvantage, it's a large factor, but it makes the whole process of Indian monsoon on seasonal timescales almost unpredictable, because internal atmospheric variability is very difficult to predict more than, let's say, a week or 2 weeks in advance. And then snow cover, land surface processes have been proposed. The North Atlantic multidecadal variability has been proposed. But our interest was to investigate then the equatorial Atlantic impact, because it's quite interesting. Okay, first look at this figure. This is the Indian rainfall year by year, starting 1900 and then going after 2000, shown here in the bars. And the colors indicate...
Fred, we are not able to see the second slide.
Oh.
Yeah, you have to move, I think. You have to move your slide.
I move, but I don't know how. You cannot see when I forward the slide?
Yeah, I'm just seeing only the first slide.
The first slide?
Yeah.
Whew. So how? Thank you very much. I don't know. Oh, wait. I will try. Okay. Let me do this. Can you see now?
No, not yet. Not yet. I go to the share presentation box.
Maybe I have to escape. Okay.
Yeah, maybe. Yeah.
Maybe I go back. I go back to.
Yeah.
This is very embarrassing. Okay.
No problem. Yeah.
Because I do stop presenting and I go present again.
Yeah. Present now.
Present now, share a window.
Yeah. When you press the box with an arrow, present now, you will see three options. Okay. A window and an entire screen and a tab.
Yes.
Yeah. And press the window. Yeah. Press the middle one, a window.
The window. Okay.
Yeah. And then select the presentation.
No, this will take ages.
You are able to see that? Yeah. No problem.
This is so small. Okay. Let me try it again.
Yeah. First of all, you open the presentation. Okay. You open the presentation.
It says now, okay, present a window, and it says I don't have permission.
Yeah, no. You first open the presentation. You open the presentation.
Okay, now I will do this.
Yeah.
Thank you very much. I will
Don't minimize it. Yeah, don't minimize it. Please keep it as it is.
Okay, my presentation is now open. Now I go to the...
Now, then you click on the present now.
Present now.
Yeah.
And then I do a window.
Yes, window. Yeah. Now you click on the window.
Oh my God. It says I'm not able.
Did you do that?
It says can't share screen. You must grant permissions. Okay, I have to do something probably else. Maybe I clicked something wrong previously. Sorry.
No, very clear. Yeah, I think you should give the permission.
Yes.
Yeah.
Question is how. Okay.
Maybe, yeah, Roshni. Very clear. Yeah.
Yes, sir.
Okay, I probably clicked something wrong previously, so I tried to go, but now if I do it, I don't have the permissions, so I have to understand where I have to change these permissions. Meeting details, maybe here.
In your Gmail settings, sir.
Sorry?
In your Gmail settings, sir.
In your Gmail kella line,
Settings lo change cheyali.
in the settings.
Gmail?
Yes, sir.
I wonder if it could be
మనం షేర్ చేయొచ్చు అంటే
Should. Maybe I have to quit the whole thing and start all over again.
Yeah, you could do that.
Okay, sir.
Okay, you could do that. Join once again. Yeah. వెళ్తాను గూగుల్ దాంట్లో వీటైనా ఇచ్చాం అందులో ఏం చేయాలి జిమెయిల్ నుంచి వెళ్ళాలి
Fare questa presentazione. Non sono riuscita a fare questo ma adesso comunque ho cliccato qualcosa.
Hello, ma'am.
Che cosa
Hello.
stai usando? Che cosa stai usando? Oh,
It's
rispondi.
Google Meet.
చెప్పు ఏం చేయలేదు
Excuse me, ma'am.
Yeah.
Yeah. First, you open the presentation, ma'am, on the desktop.
No. It's a problem of permission that we don't have, but I don't know why it's using the meet on the screen.
There's a link.
Okay, ma'am.
Just wait a second. Wait a second. We'll try to sort it out.
Okay, ma'am.
Sì.
Okay, so it looks like you have to grant us the permission to share because you are holding the meeting. Okay, so you have to give us the permission to share the screen.
No, there's nothing like that. No, చెప్పు అవును అడుగు No, there's nothing like that. Yeah, permission.
Like that. Must be permission.
వాళ్ళతో మాట్లాడి మనం ఇవ్వాలా పర్మిషన్ అన్నారు Do we give permission? అవును కృష్ణ నీకు తెలీదా ఇంకో నెంబర్ నీ నెంబర్ నుంచి చెయ్యి లేవా నా దగ్గర నుంచి చేయలేకపోతే ప్రజెంట్ విండో అన్నాడా నేను అన్నానమ్మా
Alternatively, could I send you, can I try to send you the presentation?
Yeah, you can do that. Yeah.
Would that help?
Yeah. Well, it will help. It will help. Yeah. అతని పర్మిషన్ ఇవ్వలేదట నాడు చెప్పు Yeah, Fred, you can send your presentation to us.
I hope it's not too big. Okay, let me.
Yeah, Fred, can you send your presentation to us?
Yes.
Yeah. అలా ఎలా వస్తుంది ఇప్పుడు వస్తుందా మెయిల్ ఇక్కడ మెయిల్ చూసి
Let's see if this works. I'm afraid it's too big. Okay.
Yeah, no, I think there is no question like we permitting you, no problem. No, we need not give you permission because everybody has taken like that. Yeah. పరిగెత్తుకు రమ్మంటే కొంచెం అలా కాదు వాళ్ళు చేతిని చెప్తారు ఏంటమ్మా ఇప్పుడు ప్రొసీజర్ ఏంటి మామూలుగా యూట్యూబ్లో వెళ్ళిపోవచ్చు ఆయన యూట్యూబ్లో వెళ్ళొచ్చా పోనీ ఆయన వెళ్ళకూడదా
I'm trying to sending Rashmita the presentation by WhatsApp.
WhatsApp? Okay.
Yes, sir.
Yeah.
Yeah, I'm waiting that it's going through.
ఇప్పుడు ఈ అడ్రస్ ఏంటన్నా గూగుల్ డాట్ మీకేనా ఏదమ్మా కొంచెం ఇక్కడ ఎక్కడ ఉంది తల్లి సివి నాయుడు గారు ఇది మన
Did something arrive?
Yeah.
Yes, sir, it is downloading.
Yeah. You are downloading your presentation. Master చేయాలి ఇదేదమ్మా తల్లి ఇదేదమ్మా
What, sir?
No. So can you manage to show the presentation? Hello?
Yes, sir.
Will you manage to show the presentation?
Yes, sir. Yes, sir. Still it is downloading, sir. Just 1 minute.
Oh, okay, it's slowly downloading, okay.
Yes, sir. Yes, sir.
Well,
పవన్ చెప్పు హలో ఓకే ఓకే ఆయన సిస్టమ్ సెట్టింగ్స్ అడగవా కొంచెం ఏ సిస్టమ్ వాడుతున్నారో అది చెప్తాం అడుగు
Excuse me, sir.
విచ్ సిస్టమ్ యూఆర్ యూజింగ్ అని అడుగు
yes?
Which system you are using, sir?
ఆర్ యూ యూజింగ్ యాపిల్
What system?
Yes, sir. iPhone or iPad?
No, I'm using my Mac, the Mac PC,
Mac?
laptop, notebook.
మ్యాక్ నోట్బుక్ వాడుతున్నాను
Well, so I sent the WhatsApp with my phone. No, with the laptop. Right.
Yes, sir. Got it, sir. I got it. Your email, I got it, sir. I'm downloading it.
I'm trying several times again to click on this present now button, but it says I don't have permissions. I don't know.
Ma gli hai mandato la presentazione?
Sì, ma prima ho provato ha funzionato, ma non si vedeva quando avanzavo il slide. Un problema che comunque ho già visto anche a
Dai, e poi fai di nuovo.
అలాగే
Must
పంపించారు
Perché tu l'hai fatto prima.
Sì, prima ha funzionato.
ఓకే నువ్వేం చేయాలమ్మా దాన్ని వచ్చింది కదా
Perché non usi la nostra agenda? Con quante persone sono iscritte?
Ora devo...
Excuse me, sir. Are you able to see the presentation?
Oh, yes.
Yeah.
Yes.
Next.
Okay, great. Yes, thank you.
Okay,
Now it's
sir.
working.
Yes,
So
sir.
I should tell you which slide we should go to, right?
Yes,
Say
sir.
next.
Yes, sir.
You should say next. Yeah. Now you can view the presentation.
Okay,
Yeah.
Okay, sir.
Good.
great.
Yeah.
So, okay, let's go to slide number 3
Okay.
with the elephant.
Yes. Yeah.
Okay, so sources of Enzo of monsoon variability. As I mentioned before, there are so many sources have been proposed from the equatorial Pacific, of course, Enzo, Indian Ocean, extratropical influences. But our interest was now the equatorial Atlantic, because the equatorial Atlantic actually hosts a very similar mode compared to Enzo in the Pacific. If you look at this, then on the next slide, slide number 4, we see a time series of Indian monsoon rainfall. These are the bars that you can see. And the colors are actually indicating if it's a La Nina or an El Nino event. So this is highlighting the well-known Enzo Indian monsoon relationship, where when we have a warm event, so an El Nino event, we expect dry conditions in India in general. And when we have a La Nina event, we expect wet conditions. However, you can also see there are actually many exceptions from this rule. And of course, the reason is that there can be other factors influencing the Indian monsoon and not just the tropical Pacific. So we may have many other factors that are relevant.
Can I go to the next slide?
Yes, please go to the next slide. Give me just a second. So on the next slide, we see the standard deviation or typical variation on the top panel for winter conditions. So this is the interannual typical magnitude of variation in the ocean basins, calculated over a long time series. And as you can see, this is not a big surprise. The Enzo, the Eastern Pacific region, is dominating this picture. However, the Indian monsoon, at least the summer monsoon, maybe more important summer monsoon, is going on in summer. And if you look at the bottom panel, you can see that in summer, the Enzo magnitude becomes a little bit weaker compared to winter. So it weakens a little bit. Whereas in the Atlantic, you can see that something is coming up. So there's some increase of standard deviation or typical magnitude of SST variations going on in the tropical Atlantic. And so in summer, the two basins actually, they are almost able to compete with each other. Whereas in winter, it seems that really El Nino is dominating globally the standard deviation, at least in the tropical region. In summer, the Atlantic is not as large as the Pacific, but can reach half a degree of standard deviation. So there is scope for being able to influence also the South Asian region, let's say. If you go to the next slide, slide number 5, I will very often during this presentation use what I call composites based on regression. For example, Enzo composite based on linear regression. And I just write down here the formula so people know what I'm talking about. So essentially what we are doing is we are calculating the covariance of an index, which can typically be the Nino 3.4 index, the time series, with the field of interest, which could be could be rainfall in the South Asian region or global rainfall. And this regression gives us a hint. What is the typical anomaly I expect during a typical El Nino event, let's say. So we will often use these maps. If you go to the next slide, we see an example of this. So this is now, if you look at the left side of this slide, this is again a regression map for the Nino 3 index in this case. And if we regress this index on the SSTs, on the sea surface temperatures, we see El Nino itself popping up. But if you look, so this is kind of trivial. This just shows us that El Nino, if we look at the composite for El Nino, we see El Nino. But if you look at the bottom picture, this is how now the El Nino variations are typically related to rainfall over, in this case, Africa and the South Asian and Asian region. And you see this widespread drying. This is now derived from crew observations, but you can look at any other data set. This is also for the period from 1950 to 1999, because this is from a paper a few years back. Interestingly, if you go into the tropical Atlantic and define an index that is on the right-hand side now, defined in the box that you see there and defined as the negative index in that case, you can see that there's also an influence in the African and South Asian region. The influence is a little bit more complex, whereas El Nino seems to cause a widespread drying in the South Asian region, at least in this period. It turns out maybe later this is not so clear anymore. But the tropical Atlantic in the same period, let's say in the second half of the 20th century, has caused also, if there's a warm Atlantic, tropical Atlantic going on, we also cause over central India a drying, because you should switch sign here. But the structure is much more complex. So to the north and to the south, we see opposite signals. So therefore, maybe this influence is a little bit more difficult to detect. So the aim of this presentation is in principle to explain the mechanisms how the tropical Atlantic can influence the South Asian region. Even this is completely on the other side of the Enzo impact, let's say. If the Enzo impact is probably going from the east to the west, whereas we expect that the Atlantic impact should go from the west towards the east, towards South Asia. We want to understand what's going on. So if you go to the next slide, this is the wrong, I see there is a wrong picture on the top, but that doesn't matter. So on the top, you should see a lead-lag correlation between the Nino 3.4 and the Indian monsoon. But the more important one, and that is the correct one I see, is the bottom picture, which shows us the lead-lag correlation between Indian monsoon rainfall and the Atlantic. This is the index defined in the box that you have seen before. And you can see at zero lag in the middle of this panel, the correlations become statistically significant if you look at a long enough time series. So this is again a 50-year time series. And the red line is the crew. The red triangles is the crew line. So it becomes statistically significant with a 2 months lead, and then stays at zero lead, statistically significant. It's much weaker than the Enzo monsoon relationship, but there is a statistically significant relationship. And again, we want to find out what's going on. If we go to the next slide, can you go to the next slide?
Yeah.
Okay. This is another interesting feature, actually, that the first paper we wrote on this topic was actually devoted to this problem, because we wanted to understand why the Enzo monsoon relationship was weakening. And of course, there are also hundreds of papers about this topic, that it seemed that in the late 20th century, the Enzo monsoon relationship has weakened, and that is of course bad news for seasonal forecast. And we pointed out that if both features, what we can call the Atlantic Nino, a warm tropical Atlantic, and the Pacific Nino, they try to cause the same signal over India, over central India. Both cause the drying. But if they occur, like if you see in the middle row here from the 1975 to 1999, when we look at a typical El Nino event, the tropical Atlantic was cold. That means the two signals over India would cancel each other. They would interfere negatively with each other. And so we proposed that there's this possibility that a part of the weakening of the Enzo monsoon relationship was due to this destructive interference between the signal coming from the Eastern Pacific and the signal coming from the tropical Atlantic. Of course, there are many other mechanisms that have been proposed for the weakening, like global warming or different flavors of Enzo and so on. But this is one other possibility. If we go to the next slide, here also we see from another recent study, we see a time series of the running correlation between the Indian monsoon rainfall and the tropical Atlantic SSTs. And you can see that it is statistically significant only from the 1970s onward, probably. And before, it's either weak or even switches sign. So there's a strong indication that there are important decadal variations of this relationship that should be investigated. So in this study that I show here, they speculated that perhaps global warming is increasing the strength of this relationship. But this is still a topic that is not well understood, and definitely it's not clear that it's global warming or something else that is causing the strengthening of this relationship. If you go to the next panel, the next slide, so this is kind of the sketch that we want in the next few slides then to explain what is going on, how a heating, the SST anomalies in the tropical Atlantic, the surface temperature perturbations, will cause an atmospheric heating anomaly. And this heating will cause global adjustments, just like the El Nino one. But we want to understand this picture here, because we expect to a heating in the tropical Atlantic, an upper level trough somewhere between the Arabian Peninsula and South Asia. And at the low level, the responses are very often baroclinic. So at low level, we expect exactly the opposite response with a slight shift. So at low levels, we would expect a high pressure over parts of the Arabian Sea and over India. We want to explain this picture in the sketch, kind of in the following slides. If we go to the next slide. So there are tons of papers, of course, already on this topic, but still much less than the let's say Enzo monsoon relationship. But the literature is increasing. If we go to the next slide, here we see an equation that I just want to derive here, because it will be very important for understanding the next things that we discuss. So if you take the thermodynamic equation, the top equation that you see here is the thermodynamic equation, the equation for the temperature. There is the local temperature change, the horizontal advection, and the vertical advection combined with the adiabatic heating term on the left-hand side. And on the right-hand side, we have the heating, actually, divided by the heat capacity. And so it turns out that in tropical regions, often a very good approximation under stationary conditions, so we try to leave out, if we think of long-term adjustment on a seasonal time scale, we can ignore the time derivative, but we can also ignore the horizontal advection terms. So they turn out to be much smaller, typically in tropical regions, than the vertical. So what we are left with is a stability parameter, SP, which is always positive, times omega, which is the vertical velocity in the pressure coordinate system, which is related also to a good approximation to the real vertical velocity in the Z coordinate system. And this is strongly related to the heating of the atmosphere. So if you look at the boxes down, that means that now the vertical velocity is proportional, essentially, to the heating of the atmosphere. So whenever there is heating, the only way to effectively get rid of this heating, because the atmosphere cannot always be heated, only be heated. There has to be a cooling that compensates for this to get into a stationary state. The most effective way is rising motion and the adiabatic cooling due to the rising motion, which also contains the vertical advection. And this is true for the full term, but this is also true for perturbations in vertical velocity and perturbations in heating. If we assume that the stability is in tropical regions always also very close to the moist adiabat is very, so variations in stability, at least in saturated regions, or are quite small compared to the other variations. So we can make the assumption also that the variations in the vertical velocity are very much linked to variations in the heating of the atmosphere. So this is a diagnostic relationship, which means that sometimes we can assume that a perturbation in the heating causes us a perturbation in the large scale. We are talking about large scale processes here. So this would be on scales of hundreds and thousands kilometers. We are not talking about convective scale. This is not kilometer scale. This is large scale adjustments to a heating. So there's a very good relationship. But sometimes a heating can cause a vertical velocity perturbation, and sometimes a vertical velocity perturbation can cause a heating. So this is just a diagnostic relationship, and we have to case by case try to understand. If we go to the next slide, here we see an example then what is happening in the atmosphere if we have a warm sea surface temperature perturbation. Let's think about this happening in the equatorial Atlantic. We have a warm sea surface temperature patch. This will be creating instability in the atmosphere, and so there will be more convection going on in the atmosphere. So there's a delta heating. There will be a heating, what we see kind of indicated by these clouds here. This additional heating of the atmosphere has to be compensated by an increase of the vertical velocity, in this case in that region. That will cool off then the additional heating. And that sets up a whole set of other processes. For example, we have the tropopause. The tropopause acts almost like a lid. It's not a rigid lid, but the stability, the high stability in the stratosphere acts for vertical velocity like a hit, like a lid, because the stability becomes so large that all vertical velocities will be very small. So we create upper level divergence. And upper level divergence can create all kind of other adjustment processes. Most importantly, for what we are interested in, those would be equatorial Rossby and Kelvin waves that they initiate. But they also initiate extratropical wave trains. If we go to the next slide, we try to investigate this since the real world is very complicated. So there are many complications in the real world. We try to understand what's going on with a very idealized model setting. So we use what is called an aquaplanet, where we remove all land-sea contrasts, all mountains, nothing is there. Everything is water, and much more than that, the sea surface temperature, the climatological sea surface temperature distribution is completely zonally symmetric. So there's the top panel that you see there. This is just the sea surface temperature. It's a very boring situation if you want to, but good to understand what's going on. And now on top of that, we put a sea surface temperature perturbation, in this case of 2 Kelvin, on top of this. And we compare two simulations, one where this perturbation is added, and the other one where we have added nothing. So we have just the climatological zonal symmetric SSTs. And the difference between the two will give us the impact of imposing this sea surface temperature anomaly, but we know this will also cause a heating anomaly. If we go to the next slide. So the adjustment that is going on is another approximation that we may use to understand what's going on. And the best way to do it is to look at the vorticity equation. The vorticity equation, again, approximated for tropical region, leads to something that is called Sverdrup balance, which gives us a relation between the divergent wind, which, as we just discussed, can be initiated by the heating. The heating will cause vertical motion. The vertical motion hits the top of the troposphere and causes upper level divergence. This divergence, however, according to the Sverdrup balance equation, is related to stream function and rotational winds. So any divergent wind in the tropics will lead to rotational wind. And this, you can easily insert like sine and cosine functions for the divergent winds here, and find out that the stream function field and the velocity potential field, they have to fulfill, if they satisfy this relation, an out-of-phase relationship. So if the stream function, if the velocity potential that we can think is initiated and created by the heating, so this upper level divergence is consistent with this, if you look at the left panel, is related to this negative velocity potential maximum, if you want, or velocity potential minimum. And that will cause rotational winds. And the rotational winds are shown on the right-hand side. And they are exactly out of phase. So we expect to see the maximum rotational winds adjustment to this just on the gradient of the velocity potential that we see on the left-hand side. So this is a very nice relationship between the two. And this is here for upper level. This is for upper level velocity potential and for upper level stream function. But if you look at the surface, you would expect exactly the opposite sign. As I mentioned before, we expect that the circulations initiated in the tropics by a heating are baroclinic. Because if you go back, can you go back to the previous slide? Two slides before, sorry. Yes, this one. We see that a heating perturbation will typically lead to vertical motion and therefore upper level divergence. But at the surface, exactly the opposite is happening. We get low level convergence. And so we may expect that this leads to, according to the Sverdrup balance equation, to exactly the opposite response. So if you go back to this slide again, to slide number 16, yeah. Okay, so this is what we expect. Also here, the slide is not quite what I expected. Okay, let's go to the next slide. So one possible mechanism for the adjustment to a heating is the direct upper level convergence that is surrounding this upper level divergence that we have over the heating regions. So in somewhere, if something is rising in the tropics, the air has to come down somewhere, and that will lead to drying of the atmosphere and reduce rainfall. But we found that this mechanism actually doesn't explain very well the structure of rainfall adjustment. If you go to the next slide, it's not. Can I ask something? So the slides that we see is from the PDF, right? Can you hear me? Can you open the PowerPoint instead? I also sent you the PowerPoint presentation, I think, because I realized that some slides are changed if I save them on a PDF.
Yeah, just a minute, Fred. Yeah.
Yes.
Yeah, just we are trying to open the PDF for you.
The PowerPoint would be better because on the PDF somehow, for some reason, some things got changed.
Yeah. Okay. PDF. So you want us to open the PDF or the PowerPoint?
The PowerPoint.
Okay. Okay. We are opening the PowerPoint only.
Yes.
Yes. Yeah. Yeah. Slide. Yeah. Okay. Yes. Yes. This is the one.
I don't see anything yet.
Yeah. Is this the one? Is this the one you want?
Yes. Can you go? Oh, this is the PowerPoint?
Yes, this is the PowerPoint which you have sent. Shall we open the PDF?
Please open the PDF. Maybe.
Yeah. Slow. Yeah. Independent. Open. Yeah, we are trying to open the.
Yeah.
Yeah, just a minute. Yeah.
Yes.
It's not getting open.
It's not opening?
Yeah, it's not opening.
Okay. Anyway, so let's go on with the PowerPoint. So
Yeah.
some slides are just changed, and I don't know why.
Yeah, we'll go to the PowerPoint. Okay?
Yes. Let's open the PowerPoint if the PDF is not working.
Yeah.
I will just try to.
Okay. Yeah. This one? Okay. Are you able to see?
Yes.
Yeah.
Okay.
Yeah.
So if you go to the next slide.
Yeah.
Yes. So it turned out that the rainfall response we find in the model is very well outside the regions where the heating is taking place. The rainfall response is very much related to the low-level vorticity. And that means that Ekman pumping seems to be a very good candidate for how rainfall is in remote regions adjusting to this tropical Atlantic SST variation. So it's the vorticity that is created through Sverdup balance at the low levels, then through Ekman pumping leading to a vertical motion that then again has to be compensated by a reduction, in this case for a positive heating anomaly in rainfall over the South Asian region. If you go to the next slide. This, so that would be the physical mechanism that has been proposed. We get strong baroclinic wind changes in the Indian Ocean if we have a tropical Atlantic anomaly, and these wind changes at the surface will lead to low-level divergence and sinking motion and reduction of rainfall over most parts of India. However, as we discussed, the signal is a little bit more complicated. So in the real world, the adjustments are a little bit more complicated. So this, what we see on this slide here, is the outcome of what is called maximum covariance analysis. So you try to find best matching modes in terms of covariance between one field and the other field. It's a standard statistical technique. If you do this between the global SSTs and Indian rainfall, defined in that region that we see there just over land using the Aphrodite data, you would see the El Nino signal coming up. But if you focus your region, if you just cut the region in the Atlantic, then you see this tropical Atlantic or the Atlantic Nino pattern popping up, which is then, if we are in this positive phase here, related to a reduction of rainfall over central India. But to the north and to the south, so in the northeast Indian region, it's actually an increase of rainfall, and also to the south, it's an increase. So the structure is quite complicated. And this is also, if we look at how the surface pressure looks like, related to this anticyclonic structure over the Indian and Saudi Arabian region. So that would be consistent with the theory that we have just tried to revisit. If we go to the next slide. So essentially now we have explained this feature here. We expect, if we have a heating anomaly in the tropical Atlantic induced by a positive sea surface temperature perturbation related to the tropical Atlantic Nino, we get this baroclinic response, low level, high pressure, upper level trough in the South Asian region. And that is responsible for the rainfall adjustment that we see there. If we go to the next slide, the same feature, the same wind adjustments also lead to adjustment in the Indian Ocean sea surface temperatures. So if you concentrate on the top panel from these figures here, we see an increase. If there's a tropical Atlantic warming, we also see that the sea surface temperature in the northern Indian Ocean, particularly the Arabian Sea, increase. And this is because the wind evaporation, but also some upwelling processes at the coast of Saudi Arabia will be modified by these wind adjustments. If we go to the next slide, just to compare this with the typical El Nino impact. Also El Nino, and this is now for the winter season, causes a warming of the Indian Ocean. But the structure is a little bit different. The warming is much stronger, but the structure is a little bit different and can be distinguished from the Atlantic impact. If we go to the next slide. Can you go to the next slide?
One second.
Yes.
Yeah.
Yes. So how do models do this? In this study, we've been looking at CMIP models, in this case, CMIP 5 models, how they, if we have a typical tropical Atlantic warm perturbation, what do they show in rainfall over the Indian landmass? And as you can see at the top bar plot, we expect from the observations to see the strong negative perturbation. This is what we have just discussed. But the models are doing everything you want, essentially. The ensemble mean of all models, we are looking at 28 models here, is just slightly negative, but the models are all over the place. If we go to the next slide. However, what all models do, consistent with observations, is they show that if we have a tropical Atlantic warm anomaly, also the Indian Ocean becomes warm. So the winds, there are always wind adjustment in the Indian Ocean that are consistent with this, what we just have discussed, with this weakening of the Somali jet. And they all cause some warming in the Arabian Sea region. If we go to the next slide. Here we try to distinguish good the low-level wind adjustments in the models that can reproduce the rainfall over India and the models that cannot. And we can see that it's actually slightly changes in the wind pattern are responsible for this. So it's quite a subtle teleconnection, that one between the Atlantic and the Indian monsoon, because the wind changes really here between what we call the good models and the poor models are really minor, and both cause this warming of the Indian Ocean. If we go to the next slide. However, if we look at a different, more large-scale monsoon index, which is the Webster and Young monsoon index, which is based on the vertical shear of the zonal wind. So this shear of the zonal wind is positive in the Asian region. But if we have a tropical Atlantic warm anomaly, this shear is weakening. And we see this in the bar plot down, that all models consistent with observations show even the models that are not able to reproduce the rainfall signal over India, but they are able to reproduce this large-scale monsoon adjustment of changing the wind shear. So the wind shear seems to be the impact of the wind shear in the South Asian region is a very robust feature as adjustment to the tropical Atlantic warming that all models can reproduce, consistent with the observations. If we go to the next slide, this is just another more applied study where we showed that so the Arabian Sea region, if we look on the left panel here, is the region where we have climatologically strong upwelling due to the Somali jet in the ocean. And that causes that there is a lot of chlorophyll production that is important for fish in that region. And this can be modified if we look at the right-hand side by an Atlantic event. So if we have a 1 Kelvin Atlantic cooling event, we would substantially increase the upwelling in the Arabian Sea region due to modification of the Somali jet. And so we increase chlorophyll and therefore probably fish, nutrients for fish in that region. It's just an application. If we go to the next slide, this is just showing that this is consistent also with the shoaling of the thermocline then in that region, induced by modification of the Somali jet. If we go to the next slide. This was an interesting study by Potter Binjara in 2014, but there have been follow-ups on this that show actually that the same mechanism, probably, the wind shear changes that we can explain by this gill-type response to a tropical Atlantic heating, seems to have a very strong impact on Bay of Bengal tropical cyclones in the summer season. This is probably not the most important season for very strong perturbations. However, they are very important. Bay of Bengal cyclones are very important for then rainfall over India. And there seems to be a very strong signal, much stronger than the one coming from the Pacific Nino. If we go to the next slide, we can see this in the table that only the Atlantic, if we consider warm and cold Atlantic zonal mode events, and pure ones also. So once we select Atlantic Nino events that are unrelated to Pacific events, if we can then compare the typical amount of tropical cyclones per season in the cold event compared to the warm event, we see a statistical significant change. Whereas such a change is very difficult to find if you compare La Nina and El Nino. So the Atlantic, this impact on the wind shear seems to have a very important impact for Bay of Bengal tropical cyclones. If we look on the next slide, and I think this will be the final topic. This is now looking at a decadal timescale. We look at the behavior of the Arabian Sea, mean Arabian Sea temperatures here, sea surface temperatures. And as you can see, from the 1900s to after 2000, there's of course a global warming trend. But on top of that, we see variations. And in particular, there's from the 1960s onward, or 1980s, let's say, an acceleration of this warming in the Arabian Sea. The question is, what is this due to? So we try to detrend this. If you go to the next slide, if we now correlate the Arabian Sea spring and winter temperatures with global SSTs to understand what could be the possible mechanism, we see that something in the North Atlantic again is popping up, and also in the tropical Atlantic. So the indication is that the Atlantic multidecadal oscillation or Atlantic multidecadal variability may have a very strong impact through, again, a gill-type response in the Indian Ocean on the Arabian Sea temperatures. And you see this in the bottom graph at the time series that are very much correlated, the Arabian Sea temperature time series as deviation from the trend compared to the AMO, Atlantic multidecadal oscillation signal. If we look at the following slide, the next slide, and the physical mechanism for this is actually that, again, a response in the Atlantic may be helped also by some kind of warming response that is going on in the Western Pacific, lead to wind response here seen in winter. This is for winter, the winds that we see here. So we get southerly winds, southwesterly winds that counteract the winter monsoon winds that are northeasterly. And so we reduce the evaporation in the Indian Ocean. And this reduction in evaporation in winter and spring will lead to then to the spring warming that we observe in the Arabian Sea region. And I think with this I'm finished. I don't want to go too much through this summary time series. I just want to thank very much for this opportunity. And so if you go to the next slide, it's the summary slide that maybe people can read. I don't want to go through this. We have talked already a lot. So I'm very sorry that there were these technical problems in the beginning. But perhaps because I'm not so much used to this Google Meet system. But anyway, next time I'll be better prepared. But we managed somehow to do it anyway. So I'm finished here with my presentation.
Yeah. Well, thank you, Dr. Fred Kucharski, for your interesting talk on the tropical Atlantic and Indian monsoon. Now I invite if there are any questions from the audience posted in the chat box. Yeah, I'll just wait for them. Amma, ikkada ekadana chat box unda? Ikkada? Unnaya? Okay. Fred, I have a question.
Yes.
They say most of the South Indian Ocean warming is slowly creeping into the North Indian Ocean, right? And as you said, will the Atlantic Ocean dominates, or will it dominate, or the North Indian Ocean dominates in the evolution of either tropical cyclones or in the modulation of the Indian summer monsoon? Which factor will dominate, as you think?
This is a very good question. So you say the North Indian Ocean is warming up during the summer monsoon?
Yes, just before that. Yeah.
Yes. But so this is, you say this is a seasonal feature, or is this, you consider this as a seasonal feature happening every year, or depending on the strength of the monsoon?
No, every year, you will see, I mean, just before the onset of the monsoon, you will see the ocean warming, right? And the ocean,
Yes.
is supposed to decrease the gradient between the land and the ocean, right?
Yes.
It's getting warm.
Yes.
So even though we have enough evaporation due to the warming of the ocean, we don't have a good mechanism to advect this moisture onto the mainland. Okay.
Yes, because the gradient is reduced. That's
Yes.
what you're saying.
Because,
Right.
what I mean to say here is this going to dominate, or the Atlantic, whatever you call, is going to dominate the Indian Ocean happenings?
I think, yes, I think if we have a very strong signal in the Indian Ocean itself, then the signal in the Indian Ocean will dominate, definitely. At least for the seasonal behavior, definitely. If you have I think this happened maybe last year or a few years ago, when you have a very strong warm anomaly in the northern Indian Ocean, let's say Arabian Sea.
Okay.
This is very likely to dominate the Indian monsoon response compared to the tropical Atlantic, because you're in a very warm ocean basin and you are very close. So that is very likely having a very strong impact on the Indian summer monsoon. Definitely dominating compared to the Atlantic.
Okay.
Yes. Yeah, the Indian Ocean is very important. Yes.
Yeah.
Yeah. So I would rank tropical Pacific, Indian Ocean, and only as a third player, maybe the Atlantic, tropical Atlantic.
Okay. So that's the order, is it? Right.
Yeah.
Question. Yeah. Well, if there are no questions, let's thank the speaker, Dr. Fred Kucharski. And joining me is our head of the department, Dr. C.V. Naidu, whom I request to propose a formal vote of thanks to the speaker, Dr. C.V. Naidu.
Good evening to all. I thank all the researchers and students who attended the lecture entitled Tropical Atlantic Influences on the Indian Monsoon and Indian Ocean, delivered by Dr. Fred Kucharski. Dr. Fred Kucharski is the most prominent researcher in the field of investigation of atmospheric and oceanic teleconnections and the separation of force and interannual variability of climate system. Dear sir, you have presented the most up-to-date scientific information in a way that will encourage the teaching staff, research community, and the students. We are very fortunate today to hear very informative lecture on tropical Atlantic influence. ICTP has encouraged so many researchers from our Department of Meteorology and Oceanography, Andhra University, to visit ICTP. We should be thankful for the kind support. Dear sir, there are promising students and researchers in our department. They will apply for ICTP programs. I request you to extend your help to them. I am looking forward for your kind help in the development of our Department of Meteorology and Oceanography, Andhra University. Thank you, sir. Thank you very much.
Of course. Thank you very much. We will definitely continue our collaboration. I'm pretty sure about that.
Yes, sir.
Yes, thank you very much. Very nice words. And
Also welcome.
times should improve.
Yeah.
Yes.
Yeah.
Thank
At the
you.
moment, visits are very difficult, still very difficult, but we are convinced that things will improve quickly.
Yes.
I
Yes.
wish, Fred, you should visit our Andhra University once. Okay?
Yes.
Yeah. Thank you. Very much.
Okay.
Yeah.
Okay. Thank you very much. And everybody who has a question can send me an email if someone has a question.
Yeah.
Please send me an email and then ask questions. Then I'm available to answer questions.
Right. Yes. Thank you.
Thank you very much.
Thank you.
Thank you.
Yeah.
Thank you.
Good evening. Bye.
Bye, sir. Bye, sir.
Bye bye.
Bye.